Hello. So we've all been using Rust for some amount of time. I've been using it since before 1.0, and for a long time it was a fun sort of side experiment. But what if you wanted to make it part of your everyday life? What if you wanted to bring it to work and make it the focus of your working day? So, hello, I'm Jeremy. I've been in the industry for about 30 years, mostly doing system software and at the kernel level, below the kernel, just above the kernel, mostly C, mostly C++, a bit of C++. But basically I've seen everything that can go wrong in a C program, which, as is commonly known, is a lot of things. So when I found Rust, and I'm also a PL kind of enthusiast, and so I've been experimenting with a lot of languages, but when I found Rust, it was the first programming language that genuinely solved a whole class of problems, but also could replace C in every possible role that C currently has. So I was super enthusiastic about it and started using it everywhere. 3 years ago, I joined Facebook. It was the first time I had deliberately joined a large company, and so it was an interesting experience for me to learn how large companies work, how things fit together, how technologies are used in large companies. I found that there was a lot of interest in Rust, but no one really doing anything about it. It was just sort of an ambient enthusiasm. So I thought, why not do something about this? So what does it mean to bring a new programming language to a company like Facebook? It's not really a technical matter. Like introducing a new language, just download the compiler, build something, hooray, we've introduced a new language. It's not a technical matter. It's a lot of social factors to take into account. New languages are intrinsically risky. If you're going to write some code in a new language, you're investing in that language. And if that language doesn't work out for some reason, you've just wasted some time, and worse, you may have wasted some time that turns into tech debt that you have to continuously drags on you for a long period of time. And people are fundamentally interested in getting their job done. There's enthusiasts, and they'll be enthusiastic about anything that they're enthusiastic about. But a lot of people at a job are there to work, and they've got a thing to do, and they have managers and performance bonuses and da-da-da that are all kind of attached to being able to do that thing. And so it's a risk for them to choose Rust. There has to be a good reason for them to do so. And so Rust doesn't have to be just a bit better than something else. It has to be much better at least one specific thing to even be worth their time. And it has to be generally as good as what they're currently using for everything else. So there we go. So what does much better mean? Let's say just random hand-wavy figures. Much better is that it has to be 10 times better at something than any of the incumbent languages. So Rust, what's Rust's 10x advantage in this case? Then the argument I'm going for, that I think holds pretty well, is that Rust detects large classes of serious bugs at compile time, and that detecting bugs at compile time is orders of magnitude cheaper than finding those bugs when the code has gone into production, when it's crashing in a bad way. So that all sounds good. On what grounds could I make that case to the rest of Facebook? So when I joined, I was in the source control team, and the source control team had this problem that they could see a whole bunch of curves going, and they could see at some point that the source control team, primarily the tooling is based around Mercurial, which is written in Python, and they had spent many years very thoroughly tuning that code base. So it was actually doing a surprisingly good job given the scale that it was operating at. But they could see that there was a maximum limit at which Mercurial could accept commits, which was one of the sort of primary concerns. And they could see that the curves were going to hit that rate within a couple of years. So there was going to be a hard ceiling. And one possibility would have been to just try and optimize Mercurial a bit more, rewrite bits of it in other languages, hack around. But there was also a whole bunch of functional things that Mercurial's model wasn't really accommodating. So we made the sort of architectural decision to say, let's build a whole new source control backend from scratch that not only has better performance, but unlocks a whole bunch of new capabilities. So this plan was already formed when I joined the company, and it was sort of sitting on the shelf waiting for someone to adopt it. And it was basically new source control server written in a compiled language. I went, oh, compiled language. In Facebook terms, that's really a code for C++. But I kind of was new to the company, and so I could happily ignore that and go, well, compiled language, Rust is a compiled, let's do it in Rust. And the case I made then was that a source control server correctness is like the primary requirement. Like obviously we had performance goals, but we were pretty confident we could hit those regardless just by writing it in a compiled language. But correctness was very important. Like corrupting source code, which is literally the crown jewels of the company, is a complete non-starter. So we would have to be very confident in the correctness of this new source control server before we could put it into production. And so I argued that Rust safety guarantees would give us that. And that was a very nebulous argument at that point because it was really just on faith. So we started Mononoke, and I also made the decision at that point to make it an async thing. And that was a super early adopter of Tokyo and Rust async because I started the project, I committed the first file for it on the day that Tokyo hit Crates.io. And that was just coincidence. I was going to vendor it from Git, but it hit Crates.io, and so that made it easier to do. But to even get started, I had to do a bit of groundwork. I had to make a few targeted but high-quality integrations into the environment. And I'm going to go into a bit more detail about this, but I had to integrate Rust into the build system, integrate it into the test environment, and work out a way of handling third-party dependencies with Crates.io. So 3 years later, Mononoke is now in production. It's the source of truth of one of our largest, highest throughput repos, and it's been working pretty well. And all of the Rust claims checked out. We basically spent no time debugging weird memory corruption and strange race conditions and stuff like that. And a lot of the people who'd sort of watched the project and then sort of looked at the retrospective and thought and observed that compared to a C++ program in which that would have been the normal last few months of going into production, that was remarkable. There are still core dumps in production, but they're kind of interesting sources. One of them is Stack Overflows. One of them is just unhandled C++ exceptions crossing the FFI boundary. And the rest are just buggy C++ code. And there isn't too much of that, to be honest, but the Stack Overflows one was the most interesting from my point of view. And so that was a successful enough project that the rest of the source control team has adopted Rust for all new code development, and they've been incrementally converting a lot of the existing Python code in Mercurial to, well, essentially to a new source control system that's written in Rust. This focus thing is annoying. All right, so what is the environment that I'm talking about here? Like, what does a Facebook code base look like? And I'm specifically talking here about back-end code bases, like where our sort of back-end services live that are not directly visible to the front side of either your apps or your the website. The primary languages in there are C++, Java, and Python. Like most of the back-end services are written in C++. A lot of the kind of analysis stuff is in Java, and there's tons of Python just gluing things together. But those are the three main languages. It's a highly polyglot code base. There are lots and lots of languages in use. In general, teams have a lot of freedom to choose what technologies and what languages they wish to use. And so they do. And so we have OCaml and Haskell and R and even bits of D in there. But normally, when teams choose a language, they have a very good reason to do so. They're very pragmatic. Like, they can choose whatever they want, but someone's going to come along and say, are you sure you wanted to use, say, brainfuck for this project? Like, well, it's got a really good debugging environment, so. It's a huge code base. We have a single great big monorepo that, well, we have multiple monorepos. We like them a lot, but we are hoping to get it to be one monorepo eventually. But it's got millions of files in it, hundreds of millions of lines of code, all just scattered across many, many directories. And we have a sort of general tooling goal. Like we have, obviously that is just not going to work. If you made a regular Git repo of that size, checked it out, tried to rumble around and use that, it wouldn't work. So we spend a lot of investment on tooling with a general goal that the amount of time you spend waiting for things to happen should be proportional to the size of your project, not to the size of the entire repo. And as the repo grows, if your project stays the same size, it should still take about the same time to get things done. One of the important tools in there is Buck, the build system, which builds a dependency graph across the entire source base. And so when you say build this specific target, it knows how to build that target and all its dependencies, no matter what language they're in. So, and then there's a whole bunch of production side stuff as well to monitor things and deploy them and blah, 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 blah. So, by contrast, let's look at the Rust view of the world, like as a way of getting to how does Rust fit into all of this. So I think unambiguously the first rule of Rust is safety. Like safety is a foundation of everything else. Without safety, nothing else is really worth talking about. But it's a new language, so there's a lot of scope for experimentation, greenfield development. There's no reason why Rust has to do things the same way that everything else does. It's worth experimenting. That's offset by having a core stability. There's the stability guarantees of the language that allow continuous evolution while not breaking backwards compatibility. But again, offset by Crates.io, this incredibly vibrant environment with lots and lots of third-party things in which experiments can happen and things can be tried out and accepted and adopted widely or thrown away if they don't work out. So then Cargo manages build-in dependency, and it's one of the things that newcomers to Rust regularly say. Cargo is one of the brilliant things about the Rust ecosystem. I could add a new dependency really easily. Particularly for C++ programmers, it's a revelation, but for other environments, it's pretty, it's a lovely tool. And so as a result, Cargo is kind of the center of the Rust universe. It's the thing that binds the Rust ecosystem together. And in particular, it's the thing that gives you access to Crates.io. So in order to have access to this vibrant third-party code culture, you need Cargo. But Cargo is very highly tuned towards Rust. It treats the entire universe as Rust and everything else. And everything else gets very short shrift. And in fact, you could say that supporting non-Rust is a non-goal for Cargo. Certainly, no one would. I think it would be hard to argue that you would reduce Cargo's capability as far as Rust goes in order to support something non-Rust. And so that means that in our Facebook environment, with many languages and a large repo in which almost all of it is not Rust, Cargo alone is not enough to support what we want to do. So the big question is, how do we retain Rust's essential benefits while integrating it with this larger existing ecosystem, and also get the benefits of that other ecosystem, because it's been built that way for specific reasons to support specific kinds of activities. So going back to the Rust 10x advantage, what is the cost of a bug to Facebook? Well, if you see a headline saying, Facebook down for users in X, Internally, what that turns into is, ah! And specifically, it's a lot of lost revenue. So even an hour of downtime is an ungodly amount of money. And at least some of those bugs root cause to, we traced it through, and then this program here did a use after free after this diff, and this one little innocuous change turned out to take out the entire site for 6 hours or whatever. So as a result, it behooves Facebook to spend quite a lot of money on improving code quality. And it does this in a number of different dimensions. One is like code review and static analysis and test infrastructure. And in a lot of ways, what Facebook does in these areas is world class. We spend a lot of engineering hours on these kinds of activities. And they're effective. We do see improvements. When we spend more effort on these areas, the rate of bugs goes down, mostly. But the trouble with all of these things is that they're kind of afterwards things. So the typical pattern is you write some code, you iterate, it kind of does what you think it should do, pass some local tests, you get it reviewed, you commit that to the repo, it goes into production, done. I'm going to go off and think about the next thing. And then, even code review is a pretty manual thing. So you're kind of relying, for a C++ code base, you're relying on someone to actually pay attention to every single allocation and look at all of the details. For static analysis, it can take 20 minutes, 30 minutes, half an hour, that is half an hour, an hour to come back with the result. And that may be too late. It may have gone out of your context, out of your head, and you don't really see what the implication is. And because static analysis can give you false positives, it can be quite easy to delude yourself into thinking, oh, this is definitely a false positive, it's clearly okay. And so what Rust does is by solving a large class of these problems, detecting them at compile time, it's in your inner loop. It's while you're busy working on the code, everything's in your head. When it pops up a lifetime error, you go, oh, I see, yeah, that's obvious, let's fix that up. And so by the time the code is committed, it's got at least some base level of correctness that you're not having to worry about anymore. And the nice thing about Rust is that the executables themselves operationally look like C++ executables. They're standalone, self-contained executables. So you can take that and you can drop those into a production environment expecting C++, and it more or less works the same way. But we have an open challenge here because the essence of this argument is Rust solves bugs really early. So the key question is, how can you quantify the bugs that didn't happen? How can you quantify, this bug, this might have had a bug, this particular compilation had a compilation error that, had it crept through, would have turned into a massive outage. It's very hard to do that. We're still I'm still working on how to quantify these things, because that would really help with coming up with an argument. Some of the secondary effects here are that code reviews are higher level. I sort of alluded to this earlier, but when you don't have to worry about fine-grained details of lifetimes and locking and that sort of stuff, a reviewer can just look at the code and say, well, if it compiles, all of that stuff is basically correct. Let's look at the high-level design. Is this actually the right way to fit this code together? Is this actually, the correct design? And, whatever scale you want to look at. But it means that the amount of reviewer attention is much more sort of intellectually engaging, and you get higher quality reviews, which helps a lot. It's in essence, why is this diff like it is, rather than how it works. Though obviously how it works is important, but you don't have to worry about the correctness aspect of that. And there's also a maintenance improvement. One of the biggest risks is not when the code is originally written, because the person who wrote it is thinking deeply about that domain. They have everything in their head. They have all the context. They can probably get that code right, eventually first time, even in C++. But it's when the same engineer comes back 3 months later, 6 months later, to just drop in one little bug fix. Oh, we saw this weird little thing. Let's just drop a fix in here. And without having that complete context in their head, They can say, oh, I'm going to put it in here, not realizing that the thing that they're doing the test on for that little one-liner fix was actually freed 5 lines before. Whereas in Rust, you can just sort of make those code changes, and they either compile or they don't. And if they do compile, you have a much higher assurance that at least the fix is not going to be desperately broken. So who's actually using Rust? We've had quite a lot of people adopting Rust within the company as a result of these initial successes. Who are they? Well, surprisingly, it's been the dynamic language users. By far the most active, enthusiastic early adopters of Rust were Python programmers. They basically set themselves up a game of take my favorite Python script and convert it to Rust. And the resulting Rust looks like a Python script that's been converted into Rust. It's not at all idiomatic or pretty or anything like that, but it did compile, and as a result, it probably works because it looks exactly like the Python that also probably worked. And so this was a really great educational opportunity for a large number of engineers, or a relatively large number of engineers, to get familiarity with Rust. And they hear borrow checker and scary lifetime stuff and da-da-da. But really, they got their Python script working. It's not that scary anymore. It's, they probably had to fight with the compiler a bit to get it to compile, but having got it to compile, it worked. Whereas if you do the same thing with the C++, you get something that compiles really easily, and then it crashes. And then you look in the manual, and you look at this, and you look at that, and nothing in Python prepares you for debugging a segmentation violation, and nothing in the C++ specification prepares you for it either. You're suddenly in a completely different domain of expertise required to even get started on debugging that thing. So you just kind of walk away. We have a lot of command line interface programs. A lot of them are written in Python. Python's quite a nice language for writing those things, but the result is very unusable. Due to lots of ways in which we kind of deploy Python, it starts up very slowly. So it's quite common to have a command line interface that takes 5 seconds to show a usage message. It's very unpleasant. And obviously the Python side of things could be fixed, but if you could just sit down and write a Rust program that has a nice CLI that does the thing you want and starts up in a millisecond, then that's a huge advantage. So given that you're rewriting Python code into Rust anyway, why not use it for these interactive programs? And Rust has a secret weapon here. Clap is a very capable library, and the combination with struct.op is just magical. People really love it. You can show them, you define a structure. If you're not familiar with struct.op, it's a procedural macro that you apply to a structure, and that structure defines your command line interface. And so you can just show someone, here is a structure, this structure represents the command line interface, and the value of that structure is the command line you actually got. And you go, that's incredibly simple. That's way ahead of any technology that's, well, these commonly available technologies for other languages for doing that sort of thing. And even Python presumably could, in principle, have something similar, but I don't know that that exists. So we have all of these new Rust users in the company. How do we support them? Almost all the teams that have adopted Rust have not actually had any Rust programmers on the team at that time. They've had people who are enthusiastic about Rust, but very few people who've actually used it in any kind of intensive way. So as a result, ramp-up time has been a big concern. And it turns out that there's a kind of universal experience, which is that it takes about 2 to 3 weeks of fighting the compiler, 3 to 5 weeks of working out how to get things done, and at about 8 weeks, there's people feel actually competent and sort of reasonably capable of getting the thing done that they want to get done. That's quite dependent on the language background. People coming from functional language backgrounds have a much better time of it than people coming from Go and Java. Go and Java's sort of general model of a great big tangled heap of references in a garbage collected heap where everything can mutate everything else is a terrible starting place for anything to do with Rust. The big danger point happens sometime later, say within a month or two, in which someone says, I really understand traits now. I'm going to use them everywhere. And then suddenly you end up with a code base that's full of type parameters and type constraints and 15-line where blocks, and it takes maybe, in the best case, a week to realize that that was a disastrous mistake, but sometimes that can last for months. And the relief of just sort of like collapsing all of that complexity out is palpable. We haven't actually needed very much internal training material so far, but that's definitely changing now that the user base is changing. Mostly the people who've been doctoring Rust are intrinsically enthusiastic about Rust, so they've already found everything for themselves. But we're moving into a class of people where that's not the case. So we're having to build a community within the company that is a reflection of Rust's external community. It depends a lot on the external community being very vibrant and healthy. And one of the foundational principles of Rust, as I said before, is safety, but I see that extends into Rust's community, that the psychological safety of being able to jump in and ask questions and not get shouted at is an extremely important property that I see the Rust community trying to maintain. And so we have the same, I've been explicitly adopting the same policy internally as well. We need to bootstrap the review culture so that teams can review their own code. And we have a Rust reviewers kind of reviewer tag that you can attach to a PR, and then that allows you to sort of register yourself as someone who's good at reviewing Rust code, and you can help out a team review some of their code. But I also encourage people to join that if they're learning, because watching other reviews is quite a useful learning experience. One of the big things that we've had to do that I've been emphasizing is removing gratuitous weirdness. So even if something is not entirely compatible with the way that you might do it in Rust, doing it in a way that's compatible with the way that we do it in Facebook helps people come to the code base and understand it in a way that they might not otherwise. So for example, if you're doing a binding to a C++ API, use the same names for the Rust and the C++ sides, so that, exactly the same names, so that you can find them both with grep. And that helps people who are sort of digging through code bases to work out how the Rust code fits in. So we're getting to a point now where Rust is not just for the enthusiasts, not just for the fans. We need to reach out to the people who are very pragmatic. They have a job to get done. They have many options. Rust is one of them, and it's not obvious to them that Rust is the best option. And maybe it's not. They could be completely correct. We have lots of very strong engineers who have very fine-grained understandings of all of the trade-offs involved. But some of the arguments you can make for Rust is that undetected bugs are a huge expense. The intrinsic security aspect of it is very important for any use case where Rust might be used on untrusted data. And kind of tied to that is that the learning curve is really steep, which sounds like a bad thing, but the thing about steep slopes is that you end up higher faster. And so newcomers to Rust, once you've learned the basic language, you could then set them to write security critical code without really worrying about it too much. You audit it for unsafe and you look for egregiously wrong things, but you're then fairly confident that it can't do anything very broken. Whereas in C++, you wouldn't put someone who'd been using the language for 3 months on a security critical thing. And, there's trade-offs there, but I think it's an important point. And async is really nice. That's still a strong point, I think. And interestingly, every team that has considered using Rust so far, and this won't be true forever, but I think it's true so far, everyone who's considered Rust has ended up using it. And everyone who's adopted it so far has not regretted it. So I see that as basically strong reinforcement for why other teams should adopt it. So where are we now? We're in a place where we have a very solid starting point. There's an active community. There's several critical teams working on strategically critical software using Rust. Many of the standard APIs are available, so it's fairly easy to sit down and write new code and just expect it to work within Facebook's infrastructure. And the sort of general development experience feels good. And generally, people are enthusiastic. There's a lot of enthusiasm. But it's not the default language for any particular domain yet. Like, I think that security software ought to be Rust by default, but it's not yet. The non-enthusiasts are beginning to pay attention, but we need to make this case. We need to be convincing about it. We are making terrible use of RustDoc, and there's a bunch of other parts of the Rust ecosystem that we're not really making good use of, that we need to spend more effort on. And in general, lots of polish. There is what's there is high quality and generally quite useful, but there's rough edges and there's missing functionality. As we say in Facebook, this journey is 1% finished. But if you want to come and help, we're hiring.